Welcome, gentle traveler, to the sleepy scholar. Tonight, we turn our gaze upward, not with telescopes or instruments, but with the quiet wonder of those who have always looked to the night sky and felt something ancient stirring within. We are part of something vast, something older than memory itself. We are children of the Milky Way. Close your eyes if you wish. Let your breathing slow. Tonight, we'll wander through the spiraling arms of our galactic home, tracing the stories written in starlight, the whispers of collisions that happened billions of years ago, and the gentle promise of cosmic events yet to come. This is not a journey of urgency or conquest. This is a pilgrimage through time and space, told in the language of wonder. Before we drift deeper into the cosmic current, take a moment to settle in. If this journey brings you peace, consider subscribing to the Sleepy Scholar, where every night we explore the universe's most beautiful mysteries together. Let this be your sanctuary, a place where curiosity and calm walk hand in hand beneath infinite skies. Now, let us begin. The galaxy that holds us. Picture, if you will, a river of light stretching across the darkness. Not a river of water, but of stars, hundreds of billions of them, swirling in a grand spiral that turns so slowly no human lifetime could perceive its motion. This is the Milky Way, our galactic home, an island universe unto itself, and you are standing upon one small world orbiting one ordinary star in one of its quieter neighborhoods. But there is nothing ordinary about belonging to such a place. The Milky Way is not static, frozen like a photograph pinned to the velvet of space. It is alive with motion, with transformation, with stories written over billions of years. It breathes in gas from the cosmic web, births new stars in cold molecular clouds, and carries within its heart the remnants of smaller galaxies it has consumed across deep time. Every element in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, was forged in the furnaces of stars that lived and died within this galaxy's embrace. Tonight, we will trace 100 threads of this cosmic tapestry, 100 facts that reveal the nature of our galactic home. Some will speak of violence, collisions and explosions that reshape entire regions of space. Others will whisper of patience, of processes that unfold over timescales that dwarf human civilization. All of them, together, form a portrait of the Milky Way, dynamic, beautiful, and impossibly vast. Let us wander through these stellar gardens together, slowly, like visitors who have all the time in the universe. The cosmic collisions that shaped our home. The Milky Way did not arrive fully formed, pristine and perfect, like some cosmic sculpture. It grew, it devoured, it merged and transformed, bearing the scars and treasures of countless encounters across billions of years. Long ago, so long that no human words can truly capture the span, our galaxy consumed smaller galaxies. Not through malice, but through the inexorable pull of gravity, the force that binds the universe together. These smaller galaxies, dwarf companions that wandered too close, were torn apart by tidal forces, their stars scattered and absorbed into the Milky Way's structure. But they did not disappear entirely. They left behind signatures, ghostly trails called tidal streams that still flow through our galaxy like rivers of ancient starlight. Astronomers call these streams stellar archaeology. By tracing the orbits and chemical compositions of stars within these streams, scientists can reconstruct the history of galaxies that died billions of years ago, yet whose stars still shine in our night sky. These are memorial lights, tributes to worlds that once were, now forever woven into our galactic tapestry. And this story of absorption and merger is not finished. Far from it. 4.5 billion years from now, in a future so distant that our sun will have swollen into a red giant and consumed the inner planets, the Milky Way will face its greatest transformation yet. The Andromeda Galaxy, our nearest large galactic neighbor, is hurtling toward us at over 200 miles per second. This is not a collision of destruction, but of cosmic marriage, two spiral galaxies performing a gravitational dance that will last hundreds of millions of years. When they finally merge, the Milky Way as we know it will cease to exist. The two galaxies will blend, their stars intermingling like paint swirling in water, creating something new, a massive elliptical galaxy that astronomers have already named Milkomeda. The night sky for any civilizations still existing in that distant epoch will be utterly transformed, filled with twice as many stars, swirling in chaotic new patterns as the merger proceeds. But here is the beautiful paradox. Despite this collision involving hundreds of billions of stars, individual stars will almost never collide. The distances between them are so vast that they will pass through one another like ghosts, untouched, reorganized by gravity alone. It is a dance of immense violence conducted with surprising grace. This is the nature of galactic evolution, slow, patient, inevitable. The Milky Way grows not through sudden leaps, but through the steady accumulation of matter, gas drawn from intergalactic space, stars captured from passing dwarf galaxies, and the invisible mass of dark matter that holds everything together like an unseen hand. Some changes arrive quietly, like rain falling on ancient stone. Gas flows inward from the cosmic web, feeding new generations of star formation in the spiral arms. Dwarf galaxies orbit the Milky Way for billions of years before finally being incorporated, their stars mixing gradually with our own. Other changes are more dramatic. When a massive star explodes as a supernova, it sends shock waves rippling through the interstellar medium, triggering new waves of star formation while simultaneously distributing heavy elements, gold, silver, uranium, into the surrounding gas. These elements will eventually be incorporated into new stars, new planets, perhaps even new forms of life. This is how galaxies grow, through patience and violence, through quiet accumulation and explosive transformation, through the steady work of gravity operating across billions of years. As you rest tonight, imagine the Milky Way as it was 10 billion years ago, smaller, younger, already ancient but still learning its shape. Imagine the galaxies it has consumed, the stars it has birthed, the elements it has forged. We are not merely residents of this galaxy. We are its children, made from its substance, inheritors of its long and turbulent history. The ancient stars that remember. There are stars in the Milky Way older than the Milky Way itself. Let that paradox settle in your mind like snow falling on dark water. These are the ancients, the firstborn, stars that formed in primordial galaxies long before our own galaxy took its present shape. When those early galaxies were consumed by the growing Milky Way, Their stars were absorbed, carried forward through time like memories preserved in light. They orbit in our galaxy now, indistinguishable to the casual eye from younger stars, yet carrying within their light a message from the early universe. Astronomers can read these messages. By analyzing the spectrum of light from these ancient stars, they can determine their chemical composition, and thereby glimpse the conditions that existed when they were born. The oldest stars are metal-poor, meaning they contain very few elements heavier than hydrogen and helium. This poverty of metals tells us they formed in the early universe, before generations of supernovae had enriched the cosmos with heavier elements. These hypermetal-poor stars are cosmic time capsules, preserving conditions from shortly after the Big Bang, when the universe was only a few 100 million years old. They shine faintly in the outer halo of the Milky Way, far from the bright, bustling center, like elderly witnesses to creation itself who have chosen to live in quiet contemplation. Some of the most fascinating stars in the Milky Way move in retrograde orbits, traveling in the opposite direction from the galaxy's rotation. This backward motion is a fingerprint of their origins. They were not born in the Milky Way's disk, where nearly all stars orbit in the same direction like cars on a cosmic highway. Instead, they came from dwarf galaxies that approached the Milky Way at different angles, carrying their own orbital momentum. When these smaller galaxies were torn apart, their stars retained their original trajectories, creating these unusual retrograde orbits. Finding these stars is like discovering fossils embedded in rock, evidence of ancient events preserved in the present. Each retrograde star is a survivor, a refugee from a galaxy that no longer exists, now making its slow journey through a cosmos that has moved on without it. The outer halo of the Milky Way is populated by these orphans, stars that orbit in the cold darkness far from the warmth of the galactic center. Some are so distant that they complete one orbit around the galaxy in over 1 billion years, moving through the void with only their own internal heat for company. They are hermit stars, anchorites of the cosmos, and yet they remain gravitationally bound to the Milky Way, forever part of its structure despite their solitary existence. This is where stellar streams become visible, long, thin trails of stars that trace the paths of destroyed dwarf galaxies. The most famous of these is the Sagittarius Stream, a river of stars flowing around the Milky Way like a cosmic ribbon, marking the slow dissolution of the Sagittarius dwarf elliptical galaxy. Over hundreds of millions of years, the Milky Way's gravity has been pulling this smaller galaxy apart, stretching its stars into a stream that now wraps around our galaxy multiple times. When you look at a map of these stellar streams, you see the Milky Way's dinner table, the remnants of meals consumed across billions of years. Each stream tells a story of a galaxy that wandered too close, was captured by gravity's embrace, and was gradually torn apart until only this trail of stars remained. Globular clusters represent another type of ancient structure within the Milky Way. These are dense, spherical collections of stars, sometimes containing hundreds of thousands of individual stars packed into a region only dozens of light-years across. Many globular clusters are over 12 billion years old, making them among the oldest objects in the galaxy. They orbit the Milky Way in the halo, moving in elliptical paths that take them from far above the galactic plane down through the disk and back again. The stars within globular clusters all formed at approximately the same time from the same cloud of gas, making them stellar siblings bound together by gravity for billions of years. Studying these clusters helps astronomers understand the early conditions of the universe and the process of star formation in the distant past. The fact that they have remained intact for so long, despite the gravitational perturbations of passing through the galactic disk repeatedly, speaks to the strength of their internal gravity and the delicate balance that preserves them. But not all star clusters survive. Open clusters, looser associations of stars formed more recently, gradually disperse over time. Tidal forces from the Milky Way's gravity, gravitational interactions with molecular clouds, and even the internal dynamics of the cluster itself cause stars to drift away, one by one, until the cluster dissolves entirely and its member stars become indistinguishable from the general stellar population. This means that the Sun, which formed 4.5 billion years ago, almost certainly has siblings, stars born from the same molecular cloud, in the same stellar nursery, that are now scattered throughout the galaxy. Astronomers are actively searching for these solar siblings by analyzing the chemical compositions and orbital properties of nearby stars. Finding them would be like discovering long-lost family members, separated by billions of years and vast distances, yet still carrying the same chemical fingerprint from their shared birthplace. Every star has a story. Every star came from somewhere, formed under specific conditions, was shaped by the environment of its birth. The Milky Way is not a static collection of lights, but a living archive of cosmic history, where every star is a chapter and every cluster is a volume in a library billions of years in the making. As you drift towards sleep, imagine these ancient stars, still shining after all these eons, their light carrying messages from the early universe. We look up and see them not as they are, but as they were, sometimes thousands of years ago, sometimes millions. We are seeing the past, preserved in light, and by seeing it, we connect ourselves to the deep time of the cosmos. The spiral arms and the dance of density. The Milky Way is a spiral galaxy, and like all spirals, it is defined by its arms, great sweeping curves of light that wind outward from the central bulge. These arms give the galaxy its characteristic shape, visible in countless photographs and illustrations, familiar to anyone who has gazed at images of our cosmic home. But here is something remarkable. The spiral arms are not fixed structures. They are not like the arms of a windmill, rigidly attached to a central hub, rotating as a solid unit. Instead, they are density waves, regions where stars and gas temporarily bunch together, creating the appearance of an arm before moving on. Individual stars drift in and out of these arms over millions of years, like cars entering and leaving a traffic jam. This was one of the great revelations of 20th century astronomy. For decades, astronomers puzzled over a problem. If the spiral arms were composed of the same stars rotating together, those arms should wind up and disappear within a few galactic rotations, because the inner parts of the galaxy rotate faster than the outer parts. But spiral galaxies like the Milky Way have maintained their spiral structure for billions of years. How? The answer is density wave theory. The spiral arms are zones of higher density, where gas and dust become compressed by gravitational forces. This compression triggers star formation. Giant molecular clouds collapse, fragment, and ignite, creating new stars. The most massive of these stars are brilliant blue giants that illuminate the spiral arms with ultraviolet light, making them appear bright and prominent. But these massive stars have short lives, burning through their fuel in only a few million years before exploding as supernovae. By the time these stars die, they have already moved out of the spiral arm where they were born. The spiral arm itself, being a wave rather than a physical structure, has moved on as well. New stars form in the compression zone, maintaining the appearance of the arm even though the individual stars within it are constantly changing. This means that when we look at the spiral arms of the Milky Way, we are seeing the galaxy's stellar nurseries, the places where new generations of stars are being born right now, at this very moment. In vast clouds of hydrogen and dust, cold and dark, gravity is slowly pulling matter together. As these clouds collapse, they fragment into smaller clumps, each destined to become a star. When enough mass accumulates, pressure and temperature in the core rise until nuclear fusion ignites, and a new star is born. The Milky Way has several major spiral arms, each named by astronomers: the Perseus arm, the Scutum Centaurus arm, the Norma arm, the Sagittarius arm. Our Sun resides in a smaller feature called the Orion spur or local arm, a minor structure that bridges the gap between two major arms. We live in the suburbs of the galaxy, a relatively quiet neighborhood where star formation proceeds at a measured pace, without the violent intensity of the major arms. These spiral arms are not the only dynamic structures in the Milky Way. The galaxy also contains a central bar, a rectangular structure of stars extending from the core, rotating as a solid unit. This bar plays a crucial role in the galaxy's evolution, channeling gas from the outer regions inward toward the center, where it can fuel star formation and feed the supermassive black hole at the galaxy's heart. The central bulge of the Milky Way, when viewed in 3 dimensions, reveals itself to be peanut-shaped rather than spherical. This unusual structure formed over billions of years as the central bar distorted the orbits of stars, creating a bulge that extends above and below the galactic plane. It is a signature of the bar's influence, a 3-dimensional sculpture created by gravity's patient artistry. Within the spiral arms, molecular clouds reign as the dominant structures. These clouds are cold, only a few degrees above absolute zero, and dense, containing enough mass to form thousands or even millions of stars. They are hidden from visible light, cloaked in dust that absorbs optical wavelengths, but they glow in infrared and radio wavelengths, revealing their presence to astronomers with the right instruments. The largest molecular clouds in the Milky Way are called giant molecular clouds, and they can span hundreds of light years and contain hundreds of thousands of solar masses of material. Within these clouds, turbulence and magnetic fields shape the gas into intricate filaments and clumps. When a region becomes dense enough, it begins to collapse under its own gravity, and star formation begins. But star formation is not a simple, straightforward process. It is influenced by many factors: the density and temperature of the gas, the strength of magnetic fields, turbulence within the cloud, radiation pressure from nearby stars, and shock waves from supernovae. All of these forces compete and cooperate, creating a complex environment where some regions of a cloud will form stars while others remain quiescent. When massive stars form, they dramatically affect their surroundings. Their intense ultraviolet radiation ionizes the surrounding gas, creating glowing regions called HII regions, bubbles of hot plasma that expand outward, clearing away the remaining gas and dust. These regions are among the most beautiful objects in the galaxy, visible as colorful nebulae like the Orion Nebula or the Carina Nebula, where new stars are actively being born. Eventually, the most massive stars end their lives in supernova explosions, releasing tremendous energy that sends shock waves racing through the interstellar medium. These shock waves compress nearby molecular clouds, triggering new rounds of star formation. In this way, star formation becomes a self-sustaining cycle. Massive stars are born, live briefly, die explosively, and in dying, trigger the birth of new stars. The Milky Way has been engaged in this cycle for billions of years, continuously recycling gas and dust into new generations of stars. The interstellar medium, the gas and dust between stars, is not empty space. It is a complex, multi-phase environment containing cold molecular clouds, warm neutral gas, hot ionized plasma, and everything in between. Magnetic fields thread through this medium, guiding the motion of charged particles and influencing the collapse of gas clouds. Cosmic rays, high-energy particles accelerated by supernova remnants and other violent events, stream through the galaxy, occasionally striking atoms and creating secondary particles that can be detected by instruments on Earth. This interstellar medium is the ocean in which stars swim, the atmosphere of the galaxy itself. It is constantly stirred by stellar winds, supernova explosions, and the rotation of the galaxy. Material flows inward from the galactic halo, falls onto the disk, forms stars, and is returned to the interstellar medium when those stars die. The Milky Way breathes, inhaling gas from the cosmic web and exhaling it back into space, enriched with heavy elements forged in stellar cores. As you rest, imagine these spiral arms slowly turning, like the hands of an immense clock marking time on cosmic scales. Imagine the molecular clouds where new stars are forming at this very moment, invisible to our eyes but burning brightly in wavelengths our instruments can detect. The Milky Way is not a finished product, but a work in progress, constantly creating, destroying, and transforming itself. The invisible architecture of dark matter. There is more to the Milky Way than meets the eye. Far more. In fact, most of the galaxy's mass is invisible, composed of a mysterious substance called dark matter that does not emit, absorb, or reflect light. We cannot see it directly, cannot photograph it, cannot capture it in any detector yet devised. We know it exists only through its gravitational influence on the matter we can see. This revelation came gradually, through the patient work of astronomers studying the rotation of galaxies. In the 1970s, astronomer Vera Rubin made detailed observations of the rotation curves of spiral galaxies, graphs showing how fast stars orbit at different distances from the galactic center. Newtonian physics predicted that stars farther from the center should orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But Rubin found something astonishing. Stars at the edge of galaxies were orbiting just as fast as stars closer to the center. This should have been impossible based on the visible matter alone. There wasn't enough mass in the visible stars and gas to account for these high orbital speeds. The only explanation was that galaxies must be embedded in halos of invisible matter, dark matter, that extends far beyond the visible disk, containing several times more mass than all the stars and gas combined. The Milky Way is no exception. Our galaxy is surrounded by a dark matter halo that extends perhaps 1 million light-years from the center, far beyond the visible disk, which spans only about 100,000 light-years. This halo contains most of the galaxy's mass, and its gravity is what holds the Milky Way together, preventing it from flying apart as it rotates. What is dark matter? Despite decades of research, we still don't know. It doesn't interact with light, which means it's not made of atoms like ordinary matter. It doesn't emit radiation of any kind. It passes through normal matter without friction or collision. The leading candidates include exotic subatomic particles that have never been detected in laboratories, or perhaps massive compact objects like primordial black holes. Experiments around the world are searching for dark matter, trying to detect it directly or to produce it in particle accelerators, but so far it remains stubbornly elusive. Despite our ignorance about its nature, we can map dark matter's distribution by observing its gravitational effects. The motions of stars and gas, the bending of light from distant galaxies, a phenomenon called gravitational lensing, and the dynamics of galaxy clusters all reveal where dark matter is concentrated. These observations have shown that dark matter forms a roughly spherical halo around the Milky Way, with density decreasing at greater distances from the center. This dark matter halo is not uniform. It contains substructure, clumps and streams of dark matter left over from the formation of the galaxy and from dwarf galaxies that have been absorbed. Some astronomers believe that dark matter may be even more finely structured, forming tiny halos around individual stars, though this remains speculative. The existence of dark matter has profound implications for our understanding of the universe. It means that the atoms that make up stars, planets, and people constitute only about 15% of all matter. The remaining 85% is dark matter, fundamentally different from anything we've encountered in everyday experience. We live in a universe dominated by a substance we cannot see, embedded in a framework we are only beginning to understand. The Milky Way's dark matter halo also plays a crucial role in its future collision with Andromeda. When these two galaxies merge, their dark matter halos will merge as well, creating an even larger halo around the resulting elliptical galaxy. The gravitational dynamics of this merger will be dominated by dark matter, even though we will only see the visible stars and gas. In the outer reaches of the Milky Way, where the dark matter halo dominates and visible stars are sparse, the galaxy fades into invisibility. But it does not end. The gravitational influence of the Milky Way extends far into intergalactic space, binding dwarf galaxies that orbit hundreds of thousands of light-years away, pulling on the Andromeda Galaxy, participating in the gravitational dance of the local group. Dark matter is the hidden scaffolding of the cosmos, the invisible framework upon which visible structures are built. Without it, galaxies like the Milky Way could not have formed. In the early universe, dark matter began clumping together first, creating gravitational wells into which normal matter fell, eventually forming stars and galaxies. Dark matter made the universe we see possible. There is something humbling about this. The Milky Way, with all its beauty and complexity, with its spiral arms and star clusters and glowing nebulae, is merely the visible decoration on an invisible structure. We are, in a sense, living on the surface of something much larger, much more massive, and much more mysterious than we ever imagined. As you drift deeper into rest, consider this invisible presence that surrounds us, holds us together, guides our galaxy's motion through space. We are part of something we cannot see, embedded in a mystery that science is only beginning to unravel. And perhaps there is peace in that, in acknowledging how much we do not know, how much remains to be discovered, how much wonder still awaits in the darkness between stars. The heart of the galaxy, at the very center of the Milky Way, hidden behind thick veils of dust that block visible light, lies one of the most extreme objects in the known universe. A supermassive black hole called Sagittarius A*, or SGR A* for short. This black hole contains approximately 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. Its gravity is so intense that nothing, not even light, can escape once it crosses the event horizon, the boundary beyond which escape is impossible. It is a one-way door in space-time, a place where the normal rules of physics break down and the universe becomes strange beyond comprehension. We cannot see SGR A* directly, but we can observe its effects on nearby stars. Astronomers have been tracking individual stars in the galactic center for decades, watching them orbit this invisible monster. Some of these stars move at astonishing speeds. One star, designated S2, reaches speeds of over 5,000 kilometers per second at closest approach, completing an orbit in just 16 years despite being as far from SGR A* as Neptune is from our Sun. These observations provided the most direct evidence for the black hole's existence, and in 2020, the team of astronomers who made these measurements was awarded the Nobel Prize in Physics. More recently, the Event Horizon Telescope collaboration produced the first image of SGR A*, not the black hole itself, which is invisible, but the glowing ring of superheated gas that surrounds it, spiraling inward toward the event horizon. But SGR A* is surprisingly quiet for a supermassive black hole. It consumes very little matter compared to black holes in some other galaxies, producing relatively little radiation. This dormancy is fortunate for any life in the galaxy. If SGR A* were actively feeding, it would produce intense radiation that could sterilize planets across large regions of the galaxy. However, evidence suggests that SGR A* was not always so quiescent. The Milky Way may have once been an active quasar, with its central black hole consuming vast amounts of matter and blazing with luminosity that rivaled the entire galaxy. Remnants of this active phase can be seen in the Fermi-bubbles, enormous structures of gamma-ray emitting gas extending 50,000 light-years above and below the galactic plane, likely inflated by outflows from the galactic center billions of years ago. These bubbles are a testament to the black hole's violent past, when powerful jets of particles and radiation were ejected perpendicular to the galactic disk, sweeping up gas and energizing it to emit high-energy gamma rays. The Fermi bubbles were only discovered in 2010, another reminder of how much we are still learning about our own galaxy. The galactic center itself is a crowded, violent place. Stars are packed densely together, and the gravitational environment is extremely dynamic. Binary star systems that wander too close to SGRA* can be disrupted by tidal forces. One star may be captured into orbit around the black hole while its companion is flung away at high speed, becoming what astronomers call a hypervelocity star. These hypervelocity stars move so fast they can escape the Milky Way entirely, traveling at speeds exceeding 1,000 kilometers per second. They are cosmic refugees, expelled from the galactic center and now journeying into intergalactic space. Astronomers have discovered several dozen hypervelocity stars, and they represent a unique opportunity to study the extreme gravitational environment near supermassive black holes. Some stars in the galactic center also rotate incredibly fast, spinning so rapidly they complete a rotation in just a few hours. These are different from the Sun, which rotates once every 27 days. The reason for this extreme rotation is not entirely clear, but it may be related to the violent conditions in the galactic center, where stellar collisions and close encounters are more common than in the quieter regions of the galaxy. The central bulge that surrounds SGRA* has that distinctive peanut shape mentioned earlier, a three-dimensional structure created by the galaxy's central bar. This bulge is densely packed with older, redder stars, stars that formed billions of years ago when the Milky Way was young. These stars orbit chaotically, their motions influenced by the bar's gravity, creating complex dynamics that are still being studied by astronomers. Within this bulge, gas flows inward along the bar, funneled toward the galactic center where it can either form new stars or feed the central black hole. This inflow of gas is part of the galaxy's larger evolution, a process that has been ongoing for billions of years and will continue for billions more. The Milky Way draws gas not only from its own outer regions but also from the cosmic web, the large-scale structure of the universe, made of filaments of dark matter and gas that connect galaxies. Gas falls onto the galactic disk from the halo, replenishing the interstellar medium and fueling continued star formation. Without this constant inflow, star formation in the Milky Way would have ceased long ago, the available gas exhausted. But gas inflow is only one part of the story. The galaxy also experiences gas outflows, driven by stellar winds, supernova explosions, and activity from the central black hole. These outflows can remove gas from the galaxy entirely, carrying it into the halo or even into intergalactic space. The balance between inflow and outflow helps determine the rate at which the galaxy forms stars and how it evolves over time. Understanding these flows is one of the major challenges in modern astrophysics. Galaxies are not isolated systems. They exchange matter and energy with their surroundings, and these exchanges profoundly affect their evolution. The Milky Way is constantly breathing, drawing in gas, converting it into stars, and expelling enriched material back into space. As you rest, imagine that dark heart at the galaxy's center, that vast gravitational well around which everything orbits. 4,000,000 times the mass of the Sun, compressed into impossible density, warping space-time itself. It is the anchor of our galaxy, the hidden point around which 200 billion stars revolve. We orbit it too, though we are 26,000 light-years away and moving slowly on cosmic timescales. The Sun takes 230 million years to complete one orbit, a galactic year, a span of time so vast that the last time we were in this position, dinosaurs had not yet appeared on Earth. the elements within you. There is a beautiful connection between your body and the Milky Way that deserves contemplation as you drift towards sleep. Every atom in your body heavier than hydrogen was forged in the heart of a star or created in the violent explosion of a supernova. The hydrogen in your body dates back to the Big Bang, created in the first few minutes of the universe's existence. But everything else, the carbon that forms the backbone of your molecules, the oxygen you breathe, the nitrogen in your DNA, the calcium in your bones, the iron in your blood, all of it was created inside stars. Stars are cosmic alchemists. In their cores, nuclear fusion transforms lighter elements into heavier ones, releasing energy that makes stars shine. Small stars like our Sun fuse hydrogen into helium. Larger stars go further, producing carbon, nitrogen, and oxygen. The most massive stars continue the process, creating neon, magnesium, silicon, and finally iron. Iron is where the process stops for stars. Fusing iron requires energy rather than releasing it. So once a massive star's core turns to iron, fusion ceases. The core collapses in a fraction of a second, triggering a supernova explosion that tears the star apart and, in the process, creates even heavier elements: gold, silver, uranium, and all the rest. These elements are scattered into space by the supernova, mixing with the interstellar medium and eventually being incorporated into new molecular clouds. When new stars form from these clouds, they are born with a richer chemical composition than earlier generations. Planets that form around these stars contain these heavy elements, and life that arises on those planets is built from them. You are made of stardust. This is not a metaphor or poetic license. It is literal truth. The atoms in your body were forged in stellar furnaces, scattered by cosmic violence, gathered by gravity into our solar system, incorporated into the Earth, and eventually assembled into the structure we call you. This means you are not separate from the cosmos. You are part of it, intimately connected to processes that occurred billions of years ago in stars that no longer exist. When you look at the night sky, you are looking at your ancestral home, the places where the elements of your body were created. The Milky Way has been engaged in this process of nucleosynthesis, the creation of elements, for over 13 billion years. The first stars contained only hydrogen and helium, the primordial elements from the Big Bang. When those stars died, they enriched the interstellar medium with the first heavy elements. Subsequent generations of stars incorporated those elements, processed them further, and created even more. Our Sun is a third-generation star, meaning it formed from gas that had already been enriched by at least 2 previous generations of stars. This enrichment is why the solar system contains rocky planets like Earth, rich in silicon, iron, and other heavy elements. First-generation stars could not have formed rocky planets because the necessary elements did not yet exist. The distribution of elements throughout the Milky Way provides clues about its history. By measuring the chemical composition of stars in different regions of the galaxy, astronomers can reconstruct how the galaxy has evolved. Stars in the inner regions tend to be more metal-rich, while stars in the outer halo are more metal-poor, reflecting the history of star formation and chemical enrichment across the galaxy. Some of the most interesting stars are those with unusual chemical compositions. stars that formed in dwarf galaxies that were later absorbed by the Milky Way, stars that formed in special environments like the galactic center, or stars that have accreted material from companions. Each unusual composition tells a story, a chemical fingerprint that reveals something about that star's history. This is how astronomers trace the Milky Way's history of galactic cannibalism. When a dwarf galaxy is consumed, its stars carry a distinctive chemical signature that differs from stars born in the Milky Way. By identifying these chemical anomalies, astronomers can piece together which stars came from which dwarf galaxies, reconstructing merger events that occurred billions of years ago. The Milky Way will continue this process of element creation for billions of years to come. New stars will form, live, and die. Some will enrich the interstellar medium with fresh heavy elements. Eventually, the galaxy will run out of gas to form new stars, and star formation will cease. But that endpoint lies trillions of years in the future, an almost incomprehensible span of time. For now, the Milky Way remains active, vibrant, continuously transforming hydrogen into heavier elements, continuously recycling matter through the stellar life cycle. And every time a new star forms, there is a chance, however small, that planets will form around it, that conditions might be right for life to arise, and that someday a being on one of those planets will look up at the sky and wonder, as you do, about their place in this vast cosmic drama. As you settle deeper into rest, feel the weight of your body, that collection of atoms forged in stars, arranged by biology into this temporary form. You are stardust, contemplating stars, the universe becoming aware of itself. In every cell, in every molecule, you carry the history of the cosmos, the future written in motion. The Milky Way is not at rest. It moves through space at incredible speeds, carrying us and everything we know on a cosmic journey whose destination is written in gravity. Our Sun orbits the galactic center at roughly 200 kilometers per second, taking 230 million years to complete one circuit. But the galaxy itself is also moving. The entire local group of galaxies, including the Milky Way and Andromeda, is falling toward the Virgo cluster, a massive collection of galaxies about 6 to 5 million light-years away. And the Virgo cluster itself is moving toward an even larger structure called the Shapley supercluster. We are, in short, participants in a cosmic dance on the largest scales imaginable, where galaxies move in response to the gravitational pull of structures millions and billions of light-years away. The universe is not static. Everything is in motion, falling, orbiting, expanding, evolving. The most significant event in the Milky Way's future is its collision with Andromeda. This merger will fundamentally reshape both galaxies, turning two spirals into one elliptical galaxy. The process will take billions of years, proceeding in slow motion on human timescales but with stunning inevitability on cosmic ones. As the two galaxies approach, their gravitational interaction will intensify. Tidal forces will stretch both galaxies, pulling out long streamers of stars. The dark matter halos will merge first, followed by the visible matter. Gas clouds will collide, triggering intense bursts of star formation as they compress and heat. The night sky will be spectacular, filled with new nebulae and young stars. Eventually, The two supermassive black holes at the centers of each galaxy will spiral inward toward each other, eventually merging into a single, even more massive black hole. This merger will release tremendous energy in the form of gravitational waves, ripples in space-time itself that will propagate across the universe. But remember, individual stars will almost never collide. The distances between them are simply too vast. Stars will pass through the merger like ghosts, their orbits rearranged by gravity but themselves unharmed. If the Earth still exists during this merger, which is unlikely, as the Sun will have become a red giant by then, the night sky would transform, but the Sun and its planets would likely survive intact, simply finding themselves in new orbits in the merged galaxy. This is not the only cosmic event in the Milky Way's future. Over the next hundreds of millions of years, it will continue to absorb dwarf galaxies that currently orbit it. The Magellanic Clouds, two small galaxies visible from the southern hemisphere, will eventually be torn apart and incorporated into the Milky Way. Their stars will join ours, their gas will fuel new star formation. Their chemical history will become part of our galaxy's record. On even longer timescales, trillions of years, star formation will gradually cease as the galaxy exhausts its supply of gas. The stellar population will age, with massive stars dying out and only low-mass red dwarfs remaining, burning slowly for thousands of billions of years. Eventually, even these will fade, leaving behind white dwarfs, neutron stars, and black holes, stellar corpses cooling slowly in the darkness. But this far future is so distant, so removed from our current epoch, that it feels more like abstract mathematics than reality. For now, the Milky Way is alive, dynamic, engaged in the full vigor of galactic life. Stars are being born, planets are forming, and somewhere out there, perhaps other civilizations are looking up at their night skies and wondering about their place in the cosmos, just as we do. The shape of the Milky Way will continue to evolve. The bar at its center may strengthen or weaken. The spiral arms will continue their density wave dance. The warp in the galactic disk, likely caused by gravitational interactions with satellite galaxies, will persist and perhaps change. The galaxy is not a fixed structure but a fluid system, constantly responding to internal and external forces. Even the galaxy's magnetic field plays a role in this evolution. This field, generated by the motion of ionized gas in the galactic disk, influences how cosmic rays propagate, how gas clouds collapse to form stars, and how material flows throughout the galaxy. Mapping this magnetic field is a major goal of contemporary astronomy, as it provides insights into the galaxy's structure and evolution. There is something paradoxical about contemplating such vast timescales. On the one hand, the changes occurring on cosmic timescales are so slow as to be imperceptible within human experience. The Milky Way appears essentially unchanged from one generation to the next, from one century to the next, even from one millennium to the next. On the other hand, when we step back and view the galaxy's history in its entirety, we see constant transformation, mergers, bursts of star formation, the gradual chemical enrichment of the interstellar medium, the evolution of structure. We are living in one brief moment within this vast cosmic story. The Milky Way existed long before us and will continue long after. Yet we are privileged to exist in an epoch when the galaxy is still active, when stars are forming, when the universe is still young enough to be interesting. In the far future, when the last stars have burned out and the universe has grown cold and dark, our time will seem like a golden age, the spring of the cosmos, when everything was fresh and new and full of potential. As you drift towards sleep, let go of the need to hold all of this in your mind at once. The galaxy is too large, too complex, too ancient to be fully comprehended. Instead, simply rest in the knowledge that you are part of something vast, that your existence is woven into cosmic processes billions of years old, and that the future stretches out before the Milky Way with possibilities we cannot imagine. The hidden rivers of gas. Between the stars, in the spaces we often think of as empty, flows an ocean of gas and dust so vast that all the stars in the galaxy are merely islands within it. This interstellar medium, as astronomers call it, is not uniform or passive. It churns with activity, shaped by forces both gentle and violent, forming structures on scales that dwarf entire solar systems. Imagine clouds of hydrogen stretching for hundreds of light years, so cold that molecules move with glacial slowness, temperatures hovering just a few degrees above absolute zero. These are the giant molecular clouds, the nurseries where stars are born. Within them, gravity works patiently, pulling matter together over millions of years, until density and pressure reach the critical point where nuclear fusion can ignite. But these clouds do not exist in isolation. They are part of a complex ecology of gas that permeates the galaxy. Surrounding the cold molecular clouds are warmer regions where hydrogen exists in atomic form rather than molecular. Further out, in the spaces between spiral arms, lies even hotter gas, heated by stellar winds and supernova shock waves, creating bubbles and cavities in the interstellar medium. This hot gas can reach temperatures of millions of degrees, so energetic that it emits X-rays. It forms when massive stars pour out intense stellar winds throughout their lives, and especially when they explode as supernovae. These explosions create expanding shells of superheated gas that sweep up surrounding material, creating structures called supernova remnants that can persist for tens of thousands of years. The Crab Nebula is one such remnant, the debris of a supernova that exploded in the year 1054, observed and recorded by Chinese astronomers as a guest star that appeared suddenly in the sky, bright enough to be visible during daylight for several weeks. Nearly 1,000 years later, that debris field still glows, powered by a rapidly spinning neutron star at its center. The collapsed core of the star that exploded, now no larger than a city but containing more mass than the Sun. These supernova remnants do more than create beautiful nebulae. They are factories of cosmic rays, accelerating particles to nearly the speed of light and sending them streaming through the galaxy. These cosmic rays, despite their name, they are particles, not rays, carry tremendous energy and can journey across the entire galaxy before finally losing their energy through collisions with gas and dust. Some of these cosmic rays reach Earth, passing through your body at this very moment. Dozens every second, particles that may have been accelerated by a supernova explosion thousands of light years away, traveling for millions of years before arriving here. They are messengers from distant catastrophes, carrying information about the extreme physics of stellar death. The interstellar medium also contains dust, tiny solid particles, typically smaller than the wavelength of visible light. These dust grains form in the atmospheres of cool stars and in the expanding shells of supernovae, made of carbon, silicates, and various ices. Though individually tiny, collectively these grains block and scatter light, creating the dark lanes visible in images of the Milky Way, obscuring our view of the galactic center and distant spiral arms. But dust is not merely an obstruction. It plays a crucial role in star formation. Within molecular clouds, dust grains serve as tiny laboratories where atoms meet and bond, forming molecules that would have difficulty forming in the gas phase alone. Water, ammonia, methanol, and thousands of other molecules form on the surfaces of dust grains before evaporating back into the gas, enriching the chemical complexity of the interstellar medium. This molecular richness is astonishing. Over 200 different molecules have been detected in interstellar space, ranging from simple diatomic molecules like carbon monoxide to complex organic molecules containing dozens of atoms. Some of these molecules are the building blocks of life, amino acids, sugars, the components of DNA. The chemistry occurring in the interstellar medium may be laying the groundwork for biology, preparing the raw materials from which life can emerge when conditions are right. When stars form from these molecular clouds, they often create disks of gas and dust around themselves, protoplanetary disks from which planets will eventually coalesce. The chemical composition of these disks, inherited from the parent molecular cloud, determines what kinds of planets can form. Rocky planets require metals, elements heavier than hydrogen and helium. Gas giants need large reservoirs of hydrogen and helium. Water worlds require abundant oxygen and hydrogen in the form of ice. Our solar system formed from such a disk 4.5 billion years ago, inheriting its chemical composition from the molecular cloud that collapsed to create the sun and planets. That cloud, in turn, was enriched by previous generations of stars, by supernovae that scattered heavy elements, by stellar winds that mixed and processed material. The composition of your body reflects this heritage, a chain of cosmic processes stretching back to the early universe. The interstellar medium is also threaded with magnetic fields, invisible lines of force that guide the motion of charged particles and influence the collapse of gas clouds. These fields are generated by the motion of ionized gas in the galactic disk, amplified by dynamo processes similar to those that create Earth's magnetic field, but operating on vastly larger scales. Mapping the Milky Way's magnetic field is challenging because we cannot see it directly. Instead, astronomers observe its effects, the way it bends the paths of cosmic rays, the way it aligns dust grains so they polarize starlight, the way it shapes the radio emission from ionized gas. Slowly, painstakingly, a picture emerges of a large-scale field that follows the spiral arms, with smaller-scale structures and turbulence creating a complex, three-dimensional tapestry. This magnetic field influences star formation by providing support against gravitational collapse. Gas clouds that might otherwise collapse quickly are held up by magnetic pressure, allowing them to form stars more gradually. In some regions, magnetic fields may prevent star formation entirely, keeping gas clouds stable for millions of years. Understanding this interplay between gravity and magnetism is essential to understanding how galaxies like the Milky Way regulate their star formation rates. The interstellar medium is not a closed system. Gas flows in from the halo, Material ejected by supernovae and stellar winds mixes with the ambient medium, and some gas may even escape the galaxy entirely if given enough energy. These flows are difficult to trace because gas in different phases, cold, warm, hot, behaves differently and requires different observational techniques to detect. Astronomers have discovered vast structures called the Fermi bubbles and the Rosetta bubbles, enormous outflows of hot gas extending tens of thousands of light-years above and below the galactic disk. These structures may be remnants of past activity from the central black hole, or they may be created by ongoing star formation in the galactic center. Either way, they demonstrate that the Milky Way is not a closed system but actively exchanges matter with its surroundings. In the outer halo, where stars are sparse and the density of gas is extremely low, the boundary between the Milky Way and intergalactic space becomes fuzzy. There is no sharp edge, no definitive boundary where the galaxy ends. Instead, it gradually fades into the intergalactic medium, the diffuse gas that fills the space between galaxies. This gas is so thin, averaging less than 1 atom per cubic meter, that it would be considered a perfect vacuum by laboratory standards, yet it contains most of the ordinary matter in the universe. The cosmic web, the large-scale structure of dark matter and gas that connects galaxies, extends filaments toward the Milky Way. Gas flows along these filaments, falling onto the galactic disk and replenishing the interstellar medium. Without this continuous inflow, the Milky Way would have exhausted its gas supply billions of years ago, and star formation would have ceased. But the inflow is not steady. It comes in clumps and streams, sometimes arriving cold, sometimes shock-heated to high temperatures as it falls through the halo. These variations in inflow rate may cause corresponding variations in star formation rate, creating periods of intense star formation separated by quieter periods. The Milky Way's history of star formation is written in the ages and compositions of its stellar populations, and reading this history is one way astronomers reconstruct the galaxy's past. As you rest, imagine this invisible ocean surrounding the stars, this medium through which stellar winds blow and shock waves propagate, where molecules form on dust grains and magnetic fields guide the dance of charged particles. The space between stars is not empty but filled with matter and energy, with structure and complexity, with the raw materials from which future stars and planets will form. The interstellar medium connects everything in the galaxy. Gas expelled by a dying star in one spiral arm may eventually be incorporated into a new star in another arm, millions of years later. The heavy elements forged in a supernova here may find their way into a planet there. Everything is recycled, reused, and transformed through the great stellar life cycle that has been operating for billions of years. The Milky Way is our home, our origin, our future. It is the context in which all human history has unfolded, the backdrop against which we love and dream and hope and fear. Every story ever told, every song ever sung, every thought ever contemplated has occurred within this spiral galaxy, under its light, within its gravitational embrace. And now, as you drift deeper into sleep, let the Milky Way hold you as it has held countless generations before you. Let its ancient light be a lullaby, its slow rotation a gentle rocking, its vast patience a reassurance that there is time enough for everything, that the cosmos is in no hurry, that rest is not only permitted but necessary. The stars will be there tomorrow. The mysteries will remain. The questions will wait patiently for your return. For now, simply rest. Let consciousness fade like distant starlight. Let the weight of cosmic time press you gently into sleep. You have wandered far tonight through space and time, and you have earned this rest. Thank you for joining the Sleepy Scholar on this journey through the Milky Way. If these cosmic wanderings bring you peace, consider returning tomorrow night for another story, another mystery, another quiet exploration of the universe and its wonders. Until then, sleep well beneath the spiral arms of our ancient galactic home. Rest now, traveler. The cosmos keeps its vigil. The Milky Way turns on through endless night, and you are part of its song, now and always.